So your question is, it's a good question. Can we just, so this is for paired data. Can we just do x bar minus y bar? Estimate. And the answer to this question is, in spirit, you're wrong, but by algebra, you're right. So the point estimate for the differences should really be the average of the differences. So you get all of those differences value and you calculate their average. And indeed, you do this to get the x bar, and when you eventually calculate standard error, you're going to take all these differences and calculate the sample standard deviation of the differences, then divide by root n to get your standard error. You should really be doing this problem entirely, when it's with paired data, you should really be doing it entirely with this new sort of variable that you're creating, which is the variable of all of the differences. Now, that being said, note something. X bar minus y bar, I'm going to do, actually this is kind of like a proof. So if you're math people, maybe you'll like, or actually if you're math people, maybe you'll also hate this. But x bar minus y bar is this, right? Well, by the distributive property, I can kind of move that 1 over n out. And actually also by the distributive property, I can do this. I can move the sum out. Which is just equal to right? So it's a bit of a algebraic nuance that you will actually get the same answer if you just take x bar minus y bar. But I would really encourage you to, when you think about paired data, just make your column of differences and then do everything the same thing as we've always done it, except do it with these differences values. Because it worked out for x bar minus y bar, but it might not work out whenever you go to calculate like the standard deviation and other stuff. Okay, it's an excellent question. Thank you for bringing it up. In fact, I was gonna say something about this and I totally forgot, so I appreciate it. Okay, so that's why. That's why if you did it the other way, you got the same answer. It's because it works out algebraically, but think about it in terms of the differences for paired data. Okay, so any other questions on this? Nice. So let's talk about this new fun thing, the t distribution. So have any of you ever heard the phrase t-tests? I think that's, I assume that's likely something a lot of us have heard, at least heard, maybe also have done a few of them. So the t-distribution is just another probability distribution, just like the normal, just like the uniform, or any of the other ones that we've talked about. And it has it comes up in a lot of different places in statistics, and we're going to talk about, there's one application of it that we're going to learn, which is sort of like the intro to thinking about the t-distribution. So I'm going to start by kind of motivating why we might need it, and then I'm going to talk a little bit about what it is, and then I'm just going to do a lot of examples. So maybe that's, without further introduction, let me jump in. So recall, the two reasons we needed a large sample. The first was so x bar would be distributed normally by the central limit theorem. right? This is one of our big ideas. X bar is itself a random variable. It'll change values depending on the sample that we take. And this random variable will have a normal distribution if it satisfies these various assumptions for this thing called the central limit theorem. That was a big idea of this semester. And remember, one of those assumptions was that we needed a data set that was reasonably large, which we said was greater than or equal to 30. Okay? So that was one of the two reasons we need a large sample whenever we performed inference. The other reason was that so our sample standard deviation, which we called S, was a good enough goog, a good enough guess for the population standard deviation, which we called sigma. Okay, so these were the two reasons we needed a large enough sample. And I want to remind us, recall also, that when our data are normally distributed, so not X bar being normally distributed, but the sample itself. If we took a sample and it looked like that sample had a bell shape, if it had a normal distribution, or I'm going to say, or nearly normal. We do not need the central limit theorem. Yeah, that's right. Because X bar will be normally distributed automatically. Right? So we need the sample size to be large enough to use the central limit theorem. But if we had a sample where the data were already normally distributed, we wouldn't actually need the central limit theorem because X bar will be normally distributed anyway. So this was a bunch of things from all of those CLT lectures. So if we had this case where the underlying data, the sample itself had a bell shape. If we had this, we can get away with a smaller sample size. Right? Because we need a large enough sample to use the central limit theorem. If we don't have to use the central limit theorem, then we don't need that large sample, right? But we would still need it if we didn't know our population standard deviation. So, but what if we have a nearly normal small sample and also must estimate our population standard deviation sigma with our sample standard deviation S. So this is the situation I want us to think about. We have a small sample. We don't need the central limit theorem because our data is already normal, but we still don't know sigma. And remember, we needed a big enough data set to be able to say, oh, just use the sample standard deviation as an approximation of sigma. So like, we still can't really do inference in this case, but I'm going to introduce a new tool that allows us to do inference in this case, even though all of our assumptions aren't met. So let's use a definition. In small, nearly normal samples, where the population standard deviation sigma is unknown, we predict sigma with the sample standard deviation S and use the t distribution. In place of the normal. So what is the t distribution? Let's take a look. T distribution looks like this, or it looks like one of these. The dotted line in this case is the normal distribution. So that's our usual standard normal. And the solid line is the t, right? So let's take a look. The dotted line, it looks like the normal is sort of taller and skinnier, and the t is kind of squished down a little bit. And there's more area in the t's tails. So let me write that down. So notice that the t distribution has extra thick, maybe I should do it like that, tails. And this is actually precisely the correction we need. So we can't use the normal because we don't have a big enough sample size to predict the standard deviation with the sample standard deviation. But the t distribution is a specific distribution that allows us to do that. We have a small sample, we have near normality of the data, so we don't have any problem with how x bar is distributed. But we're also making an estimation on the population standard deviation with the sample standard deviation, even though our data is too small for that estimation to be really good. So what we do is we add more mass to the tails of the distribution, and it's called the t distribution. Fun fact, actually, the t distribution, you might also hear it be called the student's t distribution or the student's distribution. And the reason that is when it was first developed, it was developed by a researcher at Guinness who was working for like the beer, right? The Guinness Stout Company. And he was doing research that was allowing them to like do marketing or whatever, and they didn't want him to publish under his name because then they would know how they're using this new math. So he developed it and published the work under a pseudonym, and he just called himself Student. So it actually, this is a huge thing in statistics that came out of, I guess, Guinness. Or like, thank goodness for beer, I guess. I don't know, maybe we can just say it's because of beer that we have this math tool. I kind of like that, actually. Anyway, so this is the t distribution. And let's start talking about it. So the t distribution has an additional parameter. And by this, I just mean another input. Called the degrees of freedom. So, in df. So remember when we were working with the normal, we needed to know the mean, mu, and the standard deviation, sigma, right? These like two inputs into the normal distribution to know which normal we're talking about. The t distribution kind of has the same idea, but it has this other input called degrees of freedom. And it describes, just like how mu and sigma describe the precise form of the normal, this also describes the precise form of the t. So let's take a look at degrees of freedom. And I'll make this big because I think this picture is kind of hard to see. But you'll note that on the outer side of this picture, we have the normal distribution. So this outermost curve, the really sort of like hard shaded blue one, is what the normal is. And what you can see are the different t distributions as our degrees of freedom get smaller and smaller. So as degrees of freedom goes down, our t kind of gets fatter, like fatter in the tails, and it gets squished down. Whereas in the other direction, as t gets bigger and bigger, it looks like as our degrees of freedom gets bigger and bigger, it looks like our t is starting to get more and more normal, right? It's starting to get pulled up, the tails are starting to get skinnier. And in fact, this is true. So we notice that the larger our degrees of freedom is, the more normal-like our t distribution becomes. And in fact, the t distribution is actually equal to the normal distribution. They are the exact same when we set that degrees of freedom parameter equal to infinity. So if we were to set degrees of freedom all the way to infinity, it actually is just a normal distribution. So in fact, what we're seeing in this picture, that it looks like for smaller degrees of freedom, it's less normal, and for more degrees of freedom, it's more normal, is exactly the case. If you get more and more degrees of freedom, you're actually just gonna have a normal. And further, I'm gonna mention, when degrees of freedom is greater than or equal to 30, the t distribution is almost indistinguishable. Ooh, I hope I spelled that right. Oh, that's so many letters. From the normal distribution. All right. So now that I've kind of, this is kind of an overview of the T. I've kind of talked about it without really showing us how we would use it and why it's important. So I'm sorry if this was just a little too abstract for you. Don't worry, I am going to jump into examples, and hopefully that'll help alleviate any talking about things abstractly. That, you know, it's a difficult thing to do, but it's a good way to introduce something nonetheless. I'm going to mention before I do an example that in general, when using the t distribution, at least in every case in which we are going to use the t distribution, so when using the t distribution for inference on the mean, we set the degrees of freedom equal to n minus 1, or sample size minus 1. Okay, so this degrees of freedom parameter that I'm just kind of throwing out as like the new input for this new distribution. For every case in which we are going to use it, it's just going to be whatever your sample size is minus 1. So you should always know what the degrees of freedom should be, specifically this. Okay? So this is the t distribution. I'm about to jump into some examples. I'm going to show us how to do confidence intervals and hypothesis tests. Real quick, are there any questions on this? I guess questions that can't be alleviated by an example. All right, I will jump in, but please do interrupt me. Always interrupt me. So confidence intervals. With the t distribution. Okay. Suppose we had a sample of 19 dolphins. In Japan. I guess maybe I should say from Japan. And measured the average mercury content in their muscles. We observe the following. So I think this is our data. And, oop, wait, I didn't want to do that. I want to show you this is our data to start. So this is our data, and I'm going to note there's a little error here. There should be 2.5. So this is dolphin mercury content in muscles. And I think it's micrograms is the units. So we observe this. What we want to do a 95% confidence interval for the true population average mu. Okay, so this is our aim, this is our data. Let's check our assumptions. That we need to check before we perform a confidence interval. So this is, I'm going to say this is a simple random sample. I mean, I don't think I said, just make sure I'll make that clear. This is a simple random sample of less than 10% of the population. So I'm going to assume we have 19 dolphins. There's probably a lot more dolphins in Japan than that. So I think we're pretty safe to say less than or equal to 10%. But, so this is good. The sample size is small. So that's not good, right? We would usually hit this and be like, I only have 19 observations. I can't do anything with this, correct? But what I'm going to tell you is these data are nearly normal. So it's hard to tell that just from this table right here. And in fact, at the end of this lecture, I'm gonna give you a tool to test normality a little bit better than what I'm doing right here. But let's just say I did look at this data and it is nearly normal. And also it looks normal just because our average looks to be in the center of the max and the min. That kind of checks out. And none of these are outliers. If we look at 2 standard deviations above and below the mean, each of these are within that, each of the men and the max are each within that sort of range. So we have no outliers. It looks like it's approximately symmetric. This is looking more and more normal, but again, ultimately we really should be looking at the histogram or making a QQ plot to make that judgment call. But let's say for the purposes of my example, we do have near normality. But we don't have a large enough sample. So because they're nearly normal, X bar is normally distributed. but we don't know the population standard deviation sigma. So I should say, and n is not large enough for the sample standard deviation to be a good guess. So use S in place of sigma, use the sample standard deviation in place of the population standard deviation, and use the t distribution. Right? The t distribution is very specific to this case. When this specific thing happens, you should be using the t distribution. But other than the fact that, so we're using the t distribution, but it actually comes down to being very similar to how we did confidence intervals in all other cases. So as always, now that we've reviewed our conditions and found the situation, our confidence interval is going to be the point estimate plus or minus c times the standard error. Remember, this is the form of the confidence interval for all confidence intervals that we're going to be doing in this class. But the question is, do any of these three things, the point estimate, the c, or the standard error, do any of these things change when we're using the t distribution instead of the normal distribution? The answer is yes, but just one of them. So here, a 95% confidence interval would be, we would have as our point estimate, right? We're trying to get our best guess of the population average, and that actually doesn't change. Our best guess of the population average is still going to be the sample average x bar, which in this case is 4.4. The next thing we need is the standard error. And usually we would like that to be sigma over root n. But as I said, we don't have that, so our best guess is the sample standard deviation over root n, which in this case is 2.5 over root 19. So this didn't really change either. This is what we used to predict the standard error from before. So the standard error doesn't actually change between this and every other sort of confidence interval that we've done before now. The final thing is this critical value c. And this thing actually is going to change. So remember how we used to do this, right? The absolute value of the alpha over tooth quantile of the z distribution. Well, the z-score, excuse me, the normal distribution, what this z-score thing, we're using the normal distribution here. And that's actually why we needed x bar to be normal in the first place, so that we could say that the critical value is this z value right here. But remember, we're not using the z distribution for this confidence interval. We're using this new thing called the t distribution. So this is not actually correct. We're not going to be using the z-score here. Instead, we're going to be using the analogous thing in the t distribution. So what I want, how I'm going to write it, is the absolute value of the alpha over tooth quantile of the t distribution with a given degrees of freedom. So this is the general, let me write more what it would be in our case. We would want t, our degrees of freedom is going to be n minus 1. And our alpha over 2 in this case is 0.05 over 2, which I would write as t of, we had 19 observations, so we're going to be n minus 1 is 18, and 0.025. Close that absolute value. Ooh, that is not clear. Let me try to make that clearer. Might still not be clear, maybe a little bit more. Okay, so what is this? This is the degrees of freedom, right? And this is confidence level divided by 2. So how I would call C, I would call it the 2.5th percentile of the t distribution with 18 degrees of freedom and this can be seen as, well, what do we got here? So it's going to be on the t distribution, which looks like this. It's centered at 0. And I want to know the point on this axis. I'm going to call it the t-axis, where this area and below it is 0.025. And this value right here, whatever it is going to be this value that I need. And this is the t distribution. With 18 degrees of freedom. Right? So remember we did the same thing with the z-score, right? We wanted to know the quantile on the standard normal distribution that corresponded with the area at and below it being 0.025. We're doing it the exact same thing, except we're doing it with this new distribution called the t distribution, where we have this additional input degrees of freedom. So this is a new idea. How do we actually find this? And the answer is we're just going to use Excel again. You remember we used a norm.s.inverse to get this before? Do you remember that function when we were finding critical values? We're going to be doing the same thing here, except now there's a t.inverse function. I'm going to show that to us. It's we can find t of 18 0.025 with t dot inverse of 0.025 comma the degrees of freedom 18. So this is alpha over 2. And this is degrees of freedom. Okay. If you plug that into Excel, it'll actually just give it to you. So let me try to do it here. So what we wanted was the absolute value of t.0025 comma 18, right? Which is just going to be this Excel function right here. The absolute value of it. Which is going to be 2. If you plug this into Excel, I might show, if we have time, I'll show you how to plug this into Excel at the end of class, but it seems it's straightforward. This is the function, just plug it in and press enter, right? And I'm going to tell you it'll spit out, if you try it yourself, it should spit out 2.10092204. If you try this on your own time and it's not equal to this, you should come and see me because I think you're probably submitting it wrong. Or, maybe I'm wrong, but I think I also tried this like 2 times and it should be right. So now that we know our C values, this is equal to C, right? So we know our C value, we know our standard error, and we know our X bar. And these are all of the things that we need to make a confidence interval. So thus, we have 4.4 plus or minus 2.10092204. That's our C value, right? And this is our X bar. And then we want our standard error, which was 0.5735539, I believe, around there. So if we go ahead and do all of this arithmetic, we will get a confidence interval from here to here. And the interpretation of this confidence interval is just the same as every other confidence interval that we got. It is, we are 95% confident that the true population average mu is in this interval, or equivalently, approximately 95% of confidence intervals made this way will contain the true population parameter mu. right? These are how we thought about confidence intervals. This is how you would present it to somebody if somebody asked for a confidence interval. And this is a valid confidence interval. It's just like any other one. We just had to get to it a slightly different way as a consequence of the fact we had a small sample size and didn't know the standard deviation mean. Okay? Any questions on this?
I might have missed it.
Okay.
Were we given the sample distribution of the data, or did we have to calculate that?
Yes. So I gave you I gave you this.
Oh, okay, I missed that. Okay,
And I told
thank
you that I told you that it was normal. Really, you should be looking at a histogram and a QQ plot. This is an example I found, and I decided to use it. On my next example, I'm going to show you a histogram, and we're going to actually look at normality.
Okay, thank you.
You should be looking for that bell shape is the thing. Okay, great question. Any other questions?
For the subscript on the, like, I don't know, the notation for C, is it the degree of freedom first or the alpha over 2 first? Or does it matter?
So when I do it, I do the degrees of freedom first, but I think Excel wants it the other way around.
Okay.
It's usually, I mean, if you think about it, degrees of freedom should always be greater than or equal to 1, right? And probabilities are always going to be between 0 and 1. So just like whichever one makes sense for being a probability or being an n-1 value, choose that one. So at the end of the day, it doesn't really matter, but I usually do degrees of freedom then alpha.
Okay. Yeah.
Any other questions? Okay. So this is how you do confidence intervals with, this is how you do confidence intervals with a t-distribution. I have, on the lecture video that is now posted, actually, I've done a cheat sheet specifically for the confidence intervals, but I did not do a cheat sheet for the p-values doing hypothesis testing with the t-distribution, which is the next thing I'm about to talk about. And the reason I didn't is because I think this next topic would be a good thing for you to try to make a cheat sheet on your own, and then to verify it against like homework results to make sure what you're doing is correct. I would really like you to be able to do this process yourself, and as soon as you have mastery over doing it yourself, then you should make your cheat sheet so that you can avoid computational issues as you like do your homework in your final exam. The other thing I wanted to mention is actually in the most recent, not the lecture video I just posted today, but the lecture video that got posted yesterday, there was a mistake in it. And I wanted to make sure you were all aware that I think it was like the upper confidence bound for the non-paired data or for the paired data. It was one of the upper confidence bounds. I forgot the times by standard error in the formula, and it's wrong. So one, I would go back and check that if you already made that cheat sheet to make sure you actually have the right answer. And two, I've actually deleted that video, and in my most recent video, I sort of go over it again pretty quickly. So just PSA, be careful with that. Always check your cheat sheets to make sure they're correct. And I don't know, sorry about that. I do make mistakes as well. Okay, let's do p-values. Very nice. So, an SAT prep company has developed, I don't think about the SAT, it makes me nauseous, has developed a new course to help students prepare. The company knows that students who take their other courses on average show a 100-point improvement. They want to know if the average point improvement for their new course is different. So they take the following sample. Let's say simple random sample of 29 students. That's this picture. Okay, so here we're actually looking at the data, and I'm going to tell you that x bar is equal to 135.9. S is equal to 82.2. N is equal to 29, right? And I guess the next question, or a question we're going to have to tackle pretty soon, is this sample normal? And I'm actually, this is sort of, I'm on the fence here. I think this is either, you know, like nearly normal. I could see it nearly normal. I can also see it kind of skewed a little bit to the left. But I will say, usually when things are really skewed, you don't see, this is like a lot of mass right here. So just imagine if this was like a little bit higher, I don't think we would have called this skewed, right? But if this were a little lower, then we totally would have called it skewed, right? If this wasn't here, then yeah, that would totally be skewed. So I'm a little on the fence. I think the book actually thinks this data is nearly normal. I'm gonna say, okay, yeah, I could see this being nearly normal. I might be a little skeptical. So we're gonna move forward, assuming that this data are nearly normal, but actually as a consequence of this and some other stuff, I'm gonna show us at the end of class how to kind of better look at whether or not something is truly nearly normal. So let's say nearly normal. Okay. So we have a research question right here. They want to know if the average point change for people who took the SAT and then took their class and took it again, if that is 100 or if it is something other than 100, right? So we want to perform inference to say what we can about the research question. So let's do our usual steps. Step 1, we just make our hypotheses. These I think are pretty straightforward, and you all have been getting these on the homework, so I think we're pretty good at reading a question and determining what the hypotheses should be. In this case, our H naught is mu is equal to 100. The true population average is equal to 100. Or the alternative that it isn't equal to 100. And I'm going to let alpha be equal to 0.5 again. Our second step is the easiest one, which is just assume that our null hypothesis is true, that mu is indeed equal to 100, right? So I start by saying, okay, let's say the population average is actually 100. I'm going to set mu equal to 0. And now I'm going to see what my evidence says towards, if my evidence says that maybe that assumption wasn't actually that good, or if I don't have enough evidence to say that that assumption isn't that good. Okay, so we'll do the third step, which is the meat of the problem, which is find the p-value. Okay, so if we want to find a p-value, we first need to check our assumptions. Indeed, we have less than 10% of the total population. There are many more students who could take this class than just the people that we sampled. And this sample was a simple random sample. So it was sort of a raffle situation. Everyone had an equal chance of getting picked. And thus, we have independence, which is the first thing we do need. The other problem is that the next thing, which is a problem, is that our sample size is too small. And we don't know the population standard deviation sigma, right? But we do have that our sample is nearly normal. Okay, so when this happens, we use the t-distribution. Okay, so here, this is our t, so we'll call this the t. What we have I guess say what x bar is. We have x bar of 135.9, right? So we want to find the place on the t-distribution. T-distribution is centered here. We want to find the upper tail probability, just like we found it before on the normal. We want to take this probability and times it by 2 to get the p-value. And this is since this is a two-sided hypothesis test. Okay, and to find this probability, we calculate something called a t-score. And guess what? The t-score is exactly like the z-score. It's hilariously like the z-score. It's technically saying the exact same thing, which is just t equals x minus mu over sigma, right? I literally just took out the z and put in a t. It's not anything new. But the only thing new is that we're going to be plugging it into the t distribution this time instead of the z distribution. So what do we need? We have our mu is our null value. It's 100. The sigma we need is the sigma of x bar, which is going to be, oh, where did I put it? There you are. Which is going to be, we're going to approximate it with s over root n, which in this case is 82.2. I think that's what I said it was, right? Yeah, 82.2, and n is 29. Which is 15.264157. Okay. Thus, the t-score here is going to be our point estimate minus mu over this, our standard error, which is 135.9, the sample mean minus our null value, 100, divided by this value we just calculated, 15.264157. This is going to be approximately 2.351915. Okay, so we have a t-score. How do we get the probability under the t curve? So we want, again, we want where this is t distribution with, what is it, 29 minus 1, so it's 28 degrees of freedom, right? How do we find this probability? And the answer is we use Excel again. So we want an upper tail probability. So the probability that we want is going to be 1 minus, and the function is very similar to our norm.s.dist function. It's going to be a t.dist function. And you just put in your z-score. And then comma, your degrees of freedom. And then comma 1. Just like how we do a comma 1 for the norm.s.dist function, we have to do it again here. So this is t-score. This is degrees of freedom. This is just always 1. Okay? And if you were to do this, this would turn out to be 0.01297088. And I think we want to times this by 2, right? Because it was a two-sided hypothesis test, which, oop, I didn't actually calculate this. Let's see what that is. 0.01297088 times 2 is 0.0259417. Nice. So this is our p-value. And we go on to our final step, which is to make a conclusion. So our alpha in this case was 0.05. This is indeed greater than 0.02594176. So our conclusion is to reject. The null hypothesis. Okay? Any questions on this? Nope. All right. So that is actually all we're going to need to be able to do for the t-distribution. I would warn you all, it might be smart to get started on this next homework pretty early. Well, not only do I have you do a lot of practice with the t-related stuff, but I've sort of thrown in some stuff that is not t, and I want to see if you can distinguish if you use the t-distribution here, or if you just do what we always have been doing with the normal distribution. So in that regard, it's kind of difficult. So I would get started on it early and get some help if you need it. The other thing I want to talk about is I promised I was going to give you a way to develop normality a little bit better. So let me go ahead and show us that. If you give me a moment, I need to get up my Excel sheet, wherever the heck I put it. Okay, sorry about that. Let me share my screen. So I've created an Excel sheet to enable you to do QQ plots. So if you recall, a QQ plot looks like this. It was how we established normality previously this semester. If you wanted to know whether or not a data set were normally distributed, a data set was normally distributed, you would create a QQ plot and you would say, well, how close are my points to a straight line? And this is an example of a very excellent QQ plot where there's some variation around them, but it's not a lot. And we're very close to normality here. So if I saw a data set like this, I would say, cool, this is great. This is a great data set. Whereas I also gave an example, which is also posted on Sakai, where I showed you data that doesn't really work for a QQ plot. So I would refer you to that Excel sheet if you want to remember what's normal and what's not normal. But this is how we establish normality with this particular plot. And I made this Excel sheet so that not only can you now make QQ plots, there's like a three-step process up in this top left. Not only can you make them now for your homework and for your eventual final, but I hope you actually keep this tool. And if you ever need to make a QQ plot in the future, this thing should do it. So I will tell you, this is now a tool that you have at your disposal. I will warn you though, I think I only made it up into like, I think this is actually like 150 data points. So you can't place any more than what's in the yellow here. So if you have a data set that's a much larger than that, you're gonna have to make your own QQ plot, unfortunately. And I actually posted some R code. If you do R and you need to make a QQ plot for a larger data set, you may use the code that I posted online if you know how to use R code. Unfortunately, these are the options that I have for you. So what do? If you have some data, you place it into this column. And actually, any data that you press, this whole thing will update. The only thing you really need to do is put data in here. But I will say, if you want your histogram to still be informative, you need to change your bins. So I specifically have data that kind of ranges between 20 and 105. Let's say if you had data that kind of ranged between 800 and 900, you should just change these bins to be like, what? 800, 810, 820, right? And then you can actually use this to check it, and it'll actually update your histogram for you. Of course, the histogram looks really bad because I don't have data that ranges between 800 and 900. But note, this will automatically change the x-axis for you. So actually, if you really wanted to, you could even use this to quickly make a histogram for yourself, whenever you need to make a histogram to check your assumptions for these central limit type problems. So this is a tool for all of you. It is on Sakai. I think it's under extra stuff or something like that. So I would suggest you take a look at it. Note, yeah, our histogram looks approximately bell-shaped and our QQ plot looks great. If I was given this data, I would say, yes, my data is nearly normal. Any questions on this? No? We're good? Okay. So the final thing I'm going to do before I let you go is I'm just going to show you these two functions. The norm, the t.inverse function, and the other one, t.dist. So I think in class we had an example where we wanted to do the t.inverse, right, of 0.025, comma, the degrees of freedom 18. And you can check this value against your notes. I think I took the absolute value of it as well. So you can check this value against your notes, but that's how you would put it into Excel, and this is how you would get that C value for our confidence interval. And then I think later, let me see what the other one was. I think I did equals 1 minus t got dist of 2.351915, comma, the degrees of freedom in that case, which was 28, comma 1. And this is how you would use that function in Excel. So just like I wrote, but I thought while I was on an Excel sheet, I would show it to all of you. So that is actually it for my lecture. Thank you all for coming. I will stick around. Are there any questions on the material before I end here? Are we good? All right. So you are welcome to go. I will stick around if there are any questions on anything, but thank you, everyone.